One quick thing before we get started. I have one blue card so far. So if anybody else wants to make a public comment sometime in the next hour or so, fill out a blue card and get them to us. So I think we're missing our panel chair. Well, I think we're going to go ahead and get started. Next speaker's Dr. Pete Smith, formerly USGS. Go ahead.
Got it. Sorry about that. If we can get my slides up there, that'd be great. Okay, on the at least the last agenda that I saw, the title of my talk was Old OMR, Older Middle River Flow, or Reverse Flows. But this is really a talk more about Delta Smelt, and OMR flows and turbidity will be part of that. Oops. They just told me to point it anywhere. I'm hitting the button. Doesn't seem to want to move.
I had to point it to the back.
To the back? He told me he didn't have to.
It actually stopped working for me. Did it?
You shine the green laser in the audience's eyes over there.
The laser works. Didn't seem to be doing anything. So I thought I'd try to answer kind of the key question about has entrainment of Delta Smelt had a population level effect on the trends in the population that we've observed over the years. This to me seems like a key issue that the State Board would like to answer if they are going to set interior Delta flow standards, particularly OMR flows. And my response, I'll start off right here in the beginning and say I think it is very possible, at least in my opinion, but it is only in a certain number of years since 1980 that entrainment has been a significant issue with Delta Smelt. Whether you believe there is a population effect, or if there is not, it is hard to prove. Either way. And I do believe high entrainment can mostly be avoided without too high a water cost, and I'll get into that a little bit later. But it does take a fair amount of time in terms of staff level to manage adaptively the older middle river flow standards to avoid the entrainment events. My talk today, it won't be a lot of high-tech statistics. It's going to be a little bit more what we call EDA, or exploratory data analysis, as the statisticians like to say. And I'm going to review some of the concepts that we looked into almost 6 years ago when the biological opinion for Delta Smelt was written. And I'd like to start with talking a little bit about the trends in Delta Smelt salvage. Most of you are familiar with the two fish facilities in the South Delta, and these provide a really remarkable 2-hourly time series of salvage, a sampling program for Delta Smelt and a whole bunch of other species. They also measure the length of the species, and then they aggregate that salvage into daily, monthly, and annual totals. So a very valuable data set we get from these two fish facilities. Here you see a summary of the average Delta Smelt salvage by month for the period 1993 to 2005. So it excludes some of the later years when salvage is very low. We normally expect that we see entrainment typically in the December to June, sometimes through July period. The adults come into the Delta typically during the first flush of the year, and we see them in the salvage in the December to March time period. Spawning begins typically in mid-February through June, and we begin seeing the juvenile fish in the salvage, sometimes as early as April, but more typically in May. So the data sets we have focus on the adults and the juveniles, but I want to kind of make sure everyone is aware there is a third life stage, and that is the larval life stage that are smaller than 20 millimeters. So we're missing that in the salvage. The salvage measurements of the juvenile fish only start when they're 20 millimeters. So an important component that we actually miss in the salvage. Here you see the 36-year trends in the Delta Smelt salvage, going back from starting at 1979 to the present, and you have the adults at the top, and you have the juvenile Delta Smelt salvage numbers on the bottom. We typically focus more on the adults, and that's probably because the pumping rates are higher, typically higher seasonally during the winter months, but also because the adults in many ways set off a kind of a sequence of events. If we see the adults in the salvage, that means they've moved into the central and potentially the south delta. There then is spawning in the zone of entrainment, and that can lead to salvage of the larval and the juvenile fish later in the year. The important thing I wanted to point out there about the juvenile time series, you'll see there are certain years, 1995, 1998, 1996, 2005, even 1982-83, where there's virtually no juvenile salvage. And those are the years where we have high spring flows, and almost all of those years we've had positive old and middle river flows. So juvenile Delta Smelt, which are much more closely move with the flow in much more the same way as numerical particles, those fish are strongly affected by old and middle river flows. So in those years where we have positive old and middle river flows, we generally see very close to zero salvage. When you look, let me go back once more to the top graph. When you look at that graph, you sort of can pick out, it doesn't even take an expert to say, what are the years where it looks like there's a significant entrainment effect with Delta Smelt? And this is, I'll normalize later with population size, but just looking at the numbers, you can see 81 was a year where we really entrained a lot of fish. My little arrow there at the top is showing that we got almost 60,000 fish that were salvaged. And again, I'll talk about salvage versus entrainment a little later in the talk. Two very different things. So 81 was a year where we had very high adult salvage. Of course, there was also at least recorded very high juvenile salvage. The other year is 1988, which is an interesting one. It's right in the middle of the 6-year drought. And then the next sequence of years are those during the pod, years 2000, let's say to 2004. So those 7 years are probably the 7 most, the 7 years that if we had to rank the years and the risk on entrainment, those would be the 7. The next 3, I'd probably throw in 1982 just because of the very high adult salvage that year, even though spring flows were pretty good. It was a fairly high flow year. 85, although adult salvage doesn't look too high, that is a year where we had high old and middle river flows through the entire January to June period. That looks like a year where there could have been a risk for a population level effect. And then, believe it or not, 05 had great springtime flows, and the adult entrainment looks low, but by that time the population had gotten quite low. And as you can see, then after that, there's been very little salvage of Delta Smelt. And I think that's partly a result of managing the system well, but also the very low population levels. Whoops, sorry about that. This slide now I've superimposed. I've left the adult Delta Smelt entrainment numbers by year on the top half of the slide, and the lower half you see the full midwater trawl, and just a very kind of simple, kind of intuitive analysis of looking at these two graphs. You see that most of those years where the entrainment looks like a significant problem, there was a year-over-year change in the full midwater trawl. So if you take the 7 years I mentioned, 81, 88, 2000 to 2004, in 6 of those years, there was a decline in the full mid-border troll index that averaged 48%. The 1 year where we did not see a decline was, sorry, I keep doing that. We see is over here. We have this jog between 2002 and 2003. So there was a declining trend during the pod year, but there was 1 year where we had, an actual increase between 2000 and 2003. But that could be normal considering the high variability in the indices themselves. If you look at the other 3 years I mentioned, 85, we see a decline. Because here you see a decline in 1988. So the 3 additional years I mentioned, 82, 85, 2005, we also saw a decline in all 3 of those years that averaged 38% change. If we look at the other index, the summer tone net index, which is data collected in the late summer, that index we see pretty much the same effect. Now you're seeing the full time series of both of these indexes. A little bit of difference. We see some. I keep doing that. Sorry. A little bit of difference that we see some up and down during the pod years, but basically we see a decline during the years where it looked like entrainment effects were the greatest.
Excuse me, what is pod?
Oh, the pod stands for the pelagic organism decline. So it's the. You probably understand. Okay, then the three variables we typically look at to simulate adult delta smelt, salvage or entrainment are OMR flows, turbidity, but also the population in the South Delta. Turbidity and population in the South Delta are somewhat correlated, but not always the case. There are times when we'll have high turbidity. The fish may be gone from the South Delta. So we need to really look at all 3 of those. Let me start saying a few words about OMR flows. You've heard Matt Nabriga and a bunch of others talk about it already today. Those are the 2 gauging stations, the location of the 2 gauging stations, one on Middle River, one on Old River, adjacent to Bacon Island, which isn't labeled there. These were installed in January of 1987. They're hydroacoustic flow monitoring stations. You'll see a lot of time series on my slides and others that include data prior to 1987. Keep in mind that is not measured data. That is estimated data. We've done regression analyses normally between San Joaquin River Vernalis and exports to estimate the flow in Old and Middle Rivers. So we filled in the data set back in time earlier than 1987. So from 87 on, measured data prior to 87, earlier than 87, it's estimated data. So there could be some additional error in that data. And what you'll see, you might say, well, why do we use OMR flow? Why in place of exports? It's really a very, very different variable. As you can see on that last slide, the flow comes to the pumps from the east, from the San Joaquin River through the head of Old River, or it can come from the north, and it comes down through Old and Middle River. And of course, delta smelt are generally residing to the north of the pumps, so there's some physical reasoning behind using OMR as a flow objective. But you can see here why the OMR flow and exports are very different variables. Just take a look at one particular year, 1983, and you'll see that exports were in the middle panel there were about 9,000 CFS. So they were exporting a lot of water in a very high flow in 1983, and yet OMR flow was almost 9,000 CFS positive. So it was flowing to the north away from the pumps. And the reason, well, you can look at the bottom panel and you see San Joaquin River flows were about 27,000 CFS. So a very, very high flow period on the San Joaquin River. Now, if you look at the year, let's say 2003, you'll see similar export levels around 9,000 CFS, and you'll see OMR flows are almost 9,000 CFS to the negative, in the negative direction. And San Joaquin River flows were about 1,500 to 2,000 CFS during the winter of 2003. So you see it's a very different variable. If you just look at exports, you might think the entrainment risk in 1983 and 2003 were equal, when in fact they're far from it because we had these very strong positive flows away from the pumps in 1983. But I like to look at 3 periods. Here I show 3 2-year periods of OMR flows. January and February, where those flows are kind of influencing adult entrainment of delta smelt. And then I look at March, April, which is an interesting period because we're generally not in training we're not seeing many fish. I shouldn't say not in training, not seeing many fish in the salvage in that March, April period. Yet we know spawning typically begins in the mid-March period, so the larval fish are out there in the estuary. They're probably, if there was spawning in the South Delta, they're probably going through the fish facilities, but we don't measure them. They're probably in most cases, they're going through the louvers. So I look at the first thing you look at is those January, February flows for the adults for entrainment rich. The March, April flows I like to look at for the risk on the first spawned larvae. And then we look in May, June for entrainment both of the juvenile fish and then the larvae because spawning may go on through June. When you look at this graph, you can right away say, okay, well, where are the periods of risk? Yeah, maybe 1981. 1981 doesn't look so good. We see negative OMR flows, although not so bad in the spring, but we see negative OMR flows all 3 periods. But the 2 big periods are the 6-year drought and then the 5 or 6 years of the pod. And when I talk about the pelagic organism decline, I'm usually talking 2000 to 2005, although the 2000 to 2004 period seemed to be the greatest entrainment risk. But what's interesting, in between, when we look at these kind of high flow years here in the middle, during the 90s, from 1993 to 1999, the risk doesn't look as bad, and the flows were a lot more positive during those periods, with the one exception of 1994. Which was a kind of a drought. So we had a 6-year drought. Then we had this kind of monster high flow year, 1993. Then we had this one more drought year, 94. And then we went into this string of high flow years. Then we went into these years of the pelagic organism decline, which weren't high flow years. They had pretty good winters, nice, healthy winter pulses of flow, then somewhat low flows for most of the rest of the year. So those are the years that's the first thing we look at. But what's interesting is if you looked at those salvage slides earlier, we didn't see much salvage during those drought years. So the risk looks equal, if not greater, during these drought years than the pod years. But we didn't see much salvage. So what's going on? And that will get to the issue of turbidity. But let me spend one more minute on flows before I get to turbidity. What these old and middle river flows do is they affect what we call the zone of entrainment, the ZOE of the pumps. So in a year like 1999, where we had low winter as well as springtime flows, the zone of entrainment for the pumps, which is kind of defined here with a 3-dimensional numerical model. And this is just using particle tracking over a 45-day period and marking the regions in red, that go to the pumps. And then the dirtier color, the dirty red, there's only a percentage of the particles going to the pumps. But when we're really, and I didn't write the export levels on here, I probably should have, but when we're really cranking up the exports, we can get a zone of entrainment that looks like this. And largely what happens during these periods is when export levels exceed the flow in the San Joaquin River, let's say the San Joaquin River flow is 1 to 2,000 CFS, the flow coming down from the Delta cross channel, what we call the Delta transfer flow, which enters right here, that might be 5 or 6,000 CFS. That depends on the flow in the San Joaquin River. So we might have 7,000 CFS. If we're pumping 9 or 10, the only place it can get additional water is pulling from the confluence area. And that's when we typically see that number Q West or the flow on the San Joaquin River at Jersey Point go negative. So we start drawing water from the lower portion of the San Joaquin River. And we've done particle tracking experiments, and this just gives you a little bit of an idea of how far particles can go. I won't say this is typical. This was a simulation done in the fall of 1999, but it just shows that a particle over the course of maybe 20, 25 days can actually make its way down from, in this case, the lower Sacramento River or even near the confluence area and get down to the pumps when pumping is high. The interesting thing is, during the fall, we never see any salt. We know we are pulling some parcels of water from areas where delta smelt reside in the fall, but they don't. The fish, they're swimming fish. If they don't want to go down, if there's something not to their liking in the South Delta, they won't go down there. And whether it's low turbidities or, they want to stay in more saline water, I'm not sure which, but they don't go down there in the fall. Next thing, let me say something about turbidity. That's not a picture of a Delta Smelt, but I didn't have Delta Smelt, so I threw this in just for effect. And there's a little mysid over here, so it's trying to find its prey in this turbid water. First, let me say something about data sources. We use kind of two sources of data for turbidity. One is the fish surveys themselves. When they go out on the fish surveys once a month, they collect the Secchi depth samples, and in the recent years, they're also collecting an actual turbidity measurement. So we have either Secchi, which we can make a kind of a crude conversion into turbidity, or in more recent years, we actually have a direct measurement of turbidity in terms of NTU itself from the boat sample. So we can get spatial distributions, but they're infrequent in time. I also look at the data at Freeport, Vernalis. We have two long-term, since 1960, sediment monitoring stations. So that gives us an estimate of the sediment loads coming into the Delta, and that provides a lot of information on what becomes high turbidity levels in the Delta. And then the other piece of data that we use is, I keep doing that instead of hitting the pointer. The other piece of data is this monitoring station right in the entrance gates to Clifton Court, where since March of 1988, they've been continuously measuring turbidity on a 15-minute basis, I believe. I just want to make a point that when most of the time the high turbidity levels in the Delta come from large suspended sediment inflows from the Sacramento River. Occasionally it can be the San Joaquin River if we get high flows there. But normally it's the first flush of the year, there's a high pulse of sediment load early in the storm that comes in on the Sacramento River. During that first flush, quite often the Delta Cross Channel is closed. The regulations call for it to close at 25,000 CFS to avoid some flooding issues on the McCullamy system. So what's left open is Georgiana Slough, and that carries the high sediment concentrations from the Sacramento River into the central Delta. And then that water, especially if OMR flows are high, that can bring sediment down to the South Delta, and we'll see elevated turbidity levels in front of the pumps. Why do we think Delta Smelt, like turbid water? I mean, that's sort of a biological question that I won't answer today. But we do have evidence from the culture facility have done some experiments to indicate, the Delta Smelt like to be in the turbid water. But we also have evidence from the field. If you look at the top panel there, that shows a summary of all the sampling data collected by the fall midwater trawl from 1967 to 2008. And it took the Secchi depth samples, converted into turbidity. And you can see at very low turbidity levels, 6 and below, we almost never catch a Delta Smelt, and yet there are times when you get those low turbidity levels. As the turbidity levels increase, they seem to be more and more Delta Smelt caught in the nets. There also seems to be, a distribution based on salinity, and the kind of the peak, the catch in the fall is around the 2 PSU salinity contour. We also have evidence from the salvage facilities themselves. If we just do a very crude plot, I think actually Matt Nebriga showed a somewhat similar plot. Although I haven't normalized the data here, this just shows you the actual number, the actual salvage counts versus the turbidity on that day at the entrance to Clifton Court Forebay. You can see when you get below 10, there's very little salvage at the facilities. When you get above 10 is when most of the salvage occurs. There are times when we have high turbidity where we don't get salvage, but that could easily be there is no fish in the zone of entrainment for the pumps. Just now to give you some idea of what happens in a kind of a typical before and after of the first flush. This is the first year of the spring Kodiak trawl, which started in 2002. And what you see, if you look at the top two panels, you'll see what's kind of typical of fall conditions. The graph on the left is showing the delta smelt catches. And in this particular case, they're not, this changes from year to year, but they're usually found in that lower Sac, the confluence area, sometimes more in Sassoon Bay. Very rarely, almost not since 1981, have we seen catches in the fall upstream of Jersey Point on the San Joaquin River. So you almost see none, and you see it again in this particular year, none in the South Delta. If you look at the turbidity distributions, you can see how low the fall turbidities are typically in the Delta. They're usually in the single digits, below 10 NTU. Now, what happened in this particular year, we had a pulse flow event of about 60,000 CFS in the first week of, maybe the end of December into the first week of January. And you can see the distribution of the fish changed dramatically. Now, all of a sudden, we have fish residing here in the South Delta, much higher turbidities. We actually had an average turbidity measured at the pumps for the month of January of 30 NTU. And these are the periods when the Delta gets turbid like that we see these entrainment events. And just here's a little more information on that particular survey, just so you can put it in perspective. You can see here's the flows, about 60,000 CFS that occurred at the Sacramento River at Freeport. You also see the high turbidity that we see early in the storm. The turbidities jumped up to almost 35 NTU at the pumps, and that corresponded exactly with this entrainment event here in the first week. So the survey itself was actually taken kind of a few days after the entrainment event occurred, but the turbidities were still elevated. There was still fish in the south region. If you're interested, these kind of blips here, where the environmental water account, I think, I'm sure Steve Monosmith is familiar with this because he used to be on the EWA panels. That was some environmental water they used to kind of protect, Delta Smelt from entrainment. So they kind of shut down pumping. And so you can see here they saw a small pulse coming. They reduced exports, and you can see there was no salvage, and the salvage actually occurred later with the larger pulse. How am I doing on time, Sam? I see you watching your warm-up. That's all, okay. Just very quickly, this shows you how dramatically the turbidity can change between two different years. 1993, a wet year. 1994, a dry. This is a January. This is a January-February average. This is during January of that year. So very different. This was almost a record low entrainment year, 1994, and we got entrainment during this year. Maybe I'll skip over this, but just to briefly say, here's comparing a drought year 89 versus one of the pod years 2003, and you can see very similar OMR flows, very similar exports, low turbidity, high turbidity, low salvage, high salvage. In the period from 1993, here you're seeing the adult salvage, but only January to February. Here you're seeing the old OMR flows in January, February, and here you see the turbidity at the Clifton Court Forebay. So this kind of explains the relationship between the three. Between 1994 and 2006, except for that one drought year, 1994, we had high turbidity in the south at the pumps, in front of the pumps during all those years. But you can see as we go back into those drought years, we had very low turbidities, with the one exception of 1988. And what happened in that year, they left the Delta Cross Channel open, and that increased the flow of sediment through Delta transfer. So we had flow going through Georgiana Slough, through the Delta Cross Channel. So it increased the sediment loads to the South Delta by 150%. We had a high turbidity event, and we got that high salvage. Are there enough fish? As we take this the next step, are there enough fish in the zone of entrainment? well, we can do these population estimates. I don't like doing this, but as a matter of fact, I use B.J. Miller's numbers here, and he estimated these populations from the spring Kodiak troll numbers by subregions. This was assuming delta smelter in the surface 12 feet of the water column, expanding it entirely over the volume of the estuary. We can see that in this particular year, there really were plenty of fish that were in the zone of entrainment because the pumping was very high, and this was a period when Q West, right after the pulse flow where Q West went negative. You see a little bit more. This is now 2004. You can see some of the numbers here on these kind of crude population estimates, and the numbers that were in the South Delta, which I've here defined as the San Joaquin River on south. And you can see the times of when the surveys were. But there seems to be plenty of fish in the zone of entrainments for the pumps. I think I only have two more slides here. The question is, why is it difficult to convert salvage and the distribution to data to percent of population entrained? Well, Bruce Herbold mentioned this in his talk. We have these salvage numbers that are over near the fish facilities, but what we don't know is what the losses are across the forebay. We think they're significant, on the order of 85% or more. Gonzalo may talk a little bit more about that in the next talk. So the multiplier we typically use, and I used in the calculations I'll show you in the next slide, are a factor of about 20 for the state water project, because the louvers aren't efficient either. So you take the salvage, multiply by 20, that gives you an estimate of the total entrainment. At the CVP, it's not as bad. The multiplier I used was 8. Others have used more. I think Wim Kimmerer in his 08 entrainment paper used 30. But if you do that, you can you can come up with these estimates of percentage of the fish, the number of fish entrained, and then you can look at those population estimates. And I don't know if these numbers are right. We probably shouldn't even be doing this. No one even wants to kind of show these things, but I've done it anyway. It's showing population estimates in the 10 to 30 to maybe 03 is probably a bit of an extreme example, because this is based on the February adult population, and that was after the large entrainment event that we had in 2003. So that 40-something% number may be a bit high, but that's the kind of numbers we're talking about on the adults. And I guess the one point I'd like to make is if we hit the adults hard and then they're in the zone of entrainment in the pumps, they spawn in that region. If we then entrain those firstborn fish, the early larvae, and then we also hit the juvenile fish fairly hard, that's probably a risk. It's probably creating a population. It could be creating a population level effect. One final comment is if the DCC is open, that's what I was mentioning before, what happened in water years 1981 and 1988, the DCC was left open with a pulse of about 30,000 CFS that had carried a fairly high sediment load. That increases the sediment that comes down with that so-called delta transfer flow. So that's going to make the South Delta a lot more turbid, and that's why, in part, we had large entrainment events on those particular years. Summary: OMR flows, OMR reverse flows, turbidity in the South Delta, and then the number of delta smelt we have in the zone of entrainment for the pumps are a good predictor of salvage. Turbidity in the Delta is often highest during the first flush of winter when river inflows carry large sediment loads. Entrainment loss is most significant during years when the adult, larval, and juvenile life stages are all affected. Because no salvage data are available for larvae, either OMR flows or particle tracking models must be used to estimate the loss. In the 7 years since 1980, when entrainment losses are judged to be most significant, and I show those are the 7 years I've talked about, the formative index was down in 6 of those years by an average of 48%. If we rank the next 3 years, it was down in all 3 of those years by an average of about 38%. And I think this is it. If I can get my, but a key point is there are other years, 92, 94, 96 are examples where we had very large year-over-year declines in the full mid-mortal trawl index. And that I don't believe that had anything to do with entrainment losses. So there's other things going on. I'm not saying entrainment losses are the variable that define all the variability in the indexes. And then finally, entrainment effects on delta smelt are difficult to quantify because of uncertainty in estimating both the population size and the number of fish entrained. And I guess my one management recommendation, and this is my last slide, is when we see a large sediment load and a storm coming in, we might want to close the delta cross-channel gates a little bit early if we want to prevent the South Delta from getting turbid and maybe head off an entrainment event. The other thing that could be done is inserting, just during the beginning phases of the first flush, put one of these inflatable air bladder gates in Georgiana Slough, open it up for just a week or two. I mean, the sediment comes in quite often over a very short period, and we can reduce the turbidity levels in the South Delta significantly if we cut off that sediment load coming in through the McCullamy system in Georgiana Slough. So just an idea to think about, and that is the end. I hope I didn't go too long. I didn't even time when I started.
No, I think you're not too bad. You're going to be around for a little bit too, and you can answer questions later. So I think we'll go on with our next presentation.